Last time we looked at, without giving it a name, the Phares diagram of an integer partition. So if I start with an integer partition, for example, 5, 4, 4, 1 is a perfectly good partition of 14. I can draw it in the plane, so I could think about drawing it in the first quadrant, where I just sort of label my axes, and now I'm going to have unit squares. And I'm going to put 5 in the first row, 4 in the next, 4 in the next, and 1 in the last. And when I draw it this way, so let's maybe go out to 5, and then 2 rows of length 4, 1 of length 1. Then I can think about doing different actions on this diagram, and that can lead to interesting formulas for partitions. So here is the main diagonal, and we can think about this idea of conjugation. So conjugation is just reflecting the Phares diagram across the main diagonal. And when we do that, we end up with a new partition. That new partition I'll draw over here. So the new partition, its row lengths are given by the heights of the cells for each column over here. So this is height 4, 3, 3, 3, 1. So when I conjugate the partition 4, 4, 5, 4, 4, 1, I get the partition 4, 3, 3, 3, 1. So this act of conjugation is really interesting, and it gives us lots of different ways to think about partitions. And one natural question that comes up when we look at this is we can ask ourselves, how many fixed points does this involution have? So we can let SC of n equal the set of partitions of n such that lambda is equal to lambda prime. So we can look at the partitions and we can just ask ourselves, how many are there? So for example, we enumerated the partitions of 6 last time. Let's do that again lexicographically so that we remember how the lex order on partitions works. This is a really useful total order to put on partitions. Let's start up here. 3, 2, 1, 3, 1, 1, 1. Those are all the ones that start with a 3. Now we're going to go with a 2. Okay, how many of these are self-conjugate? So if we're looking at this idea, we can sort of draw a map between the ones that get conjugated to each other. So 6 is one long row. This becomes one long column, right? 5, 1, right? There are 2 parts, so that's going to start with a 2 and then have a bunch of 1s. So that's going to go here. 4, 2, if we just think about that's going to be the first, there are 2 parts of size at least 2, so that's going to give us 2 parts of 2 in the conjugate. So we're going to map that guy up here. And then 3, 3, that's going to be a rectangle. That's this rectangle. 4, 1, 1, that's going to be interesting. That's going to go to this guy. And this is our only self-conjugate partition. So that's the only fixed point of this involution. So this is a nice way to kind of tie things up and tie things together, is looking at these fixed points. But now suppose we want to count this set, because it's combinatorics. That's what we want to do. We want to say, what is the number of SC of n, which maybe we'll call little sc of n. How can we count this? And again, with partitions, counting things for fixed n is in general hard. But we can come up with a generating function, and we can count them for all n at once, and that turns out to be a little easier. So if we're going to do that, let's think about how we would make a self-conjugate partition. So let's get some parts for our partition. Here are some parts. So these are the different sizes for the parts that we could have, for example. Now, if we're going to decide that this is going to be our longest part is going to have size 8, okay? Actually, that's 10, sorry. Well, our longest part is going to have size 10. We could try to think about what comes next, but that's not the right thing to tell ourselves. Because this has to be self-conjugate, it's going to have to be 10 tall as well. So what we can do is take another brick of size 10, and we just connect them like this. Okay, now we've ensured that this part of our partition is going to be self-conjugate. Okay, now what part can we put next? Well, we could put a part of size 8 next. And again, if we do that, we're going to have to lock it in here. Maybe we could put a part of size 4 next. Well, oh, sorry. Why am I skipping? Size 6 will go next. And then we could do a part of size 4. And now be careful, because we're not really putting a part of size 4, are we? The length of this row is actually 7. But if we think about nesting these guys, if we tried to take another 4, if we took a 4 for this hook and we tried to take another 4, look what happens. Even before I add the hook part of it, I end up making a problem for myself because I'm sticking over the edge. That's not going to be a partition. The partition doesn't have overhang. But I could take these guys, which are smaller, and I could stick those in there, and then let's take an actual hook and finish this guy off. And let's let this be our self-conjugate partition. Because the way we built it by these hooks, we can see that it's definitely self-conjugate. And that's going to be the trick to enumerating them, is keeping that observation in mind. So we want to say what other way we could think about this. So a lot of these formulas come from counting in 2 ways. And now what we want to think about is what are the parts that I was able to use, and maybe come up with a bijection of partitions with a different paradigm. So here is my claim. Here's my theorem. It's really more of a proposition, but that's okay. SC of n is equal to P odd of n. This is self-conjugate partitions of n, and this is partitions, well, we're going to call it DOD, into distinct odd parts. Now I claim that we can actually count this one, but first let's see why these are the same. If we look over here at these partitions, when we made these hooks, because we have this length and this length are the same and they overlap by 1, this is definitely going to be an odd number. So that's where the odd parts comes from. When we're making these hooks, it has to be an odd number. And now why couldn't we use 2 hooks that both have length 4 plus 4 minus 1? Well, because then they're going to hang over. There's going to be an overhang. That's the distinct part. The fact that we couldn't use this is the distinct part. So that's why we're doing it. And now if you just think about, instead of having this self-conjugate partition, let's just unfold this partition, and we're going to make it into a really, really big partition, or a partition with lots of big parts. And now each of these parts is odd because it's going to be 2n minus 1 is the length of every row, or rather 2k minus 1. Well, this guy doesn't unfold, so we'll leave it like that. And that's what we have over here. Now, if you remember, our generating function was all about the lengths of parts. So remember, we had this generating function for p of x is equal to the sum n greater than or equal to 0, p of n, x to the n. This is equal to the product of m greater than or equal to 1 over 1 minus x to the m. And now this is telling me, taking the term from here, is telling me how many parts I have that are exactly size m. So now I've said I only want to take distinct odd parts. So how can I come up with a generating function for that? Well, that's pretty easy as long as we keep remembering what this stands for. So p distinct odd of x, let's make it a generating function, is equal to the sum n greater than or equal to 0 of p into distinct odd parts of n, x to the n. What is that? It's just going to be picking off the terms here that satisfy my constraint. So here, it's going to be the product of m odd. Okay, and now instead of having this series where I have 1 plus x to the m plus x to the 2m and so on, I'm only allowed to either take nothing of that size or one thing of that size. So I get 1 plus x to the m. And that's it. Distinct tells me that instead of getting the infinite series, I can either take the part or not. And odd is taken care of down here. So now we have a generating function for the number of partitions that are self-conjugate. So self-conjugate by itself is a nice graphical thing that we can think about, but in order to get a function for it, we need to understand it in terms of this generating function that we understand, so we need to talk about it in terms of the parts, and that's where this comes in. So this is a really useful paradigm shift, thinking about different ways to line up your partitions, and thinking about the hooks is the real trick to coming up with this one.